let's see. We're done with fluids. The homework of fluid is out. I can't even talk. My mouth is so cold. My finger's so cold. So I need everybody to just kind of breathe a lot or move and heat this room up. I got this out. This is a heater. This is how heaters used to work. If you touch this, you get both burned and shocked, right? So things were not as safe a long time ago, but I need it for my hands because I can't write right now. So we're done with fluids. The fluid homework is all out and done. So it's like 15 questions, and it's due a week from yesterday. And now we're moving on. We did simple harmonic motion last time, so we're going to finish simple harmonic motion today and get to waves. So we're just doing the interesting parts of everything. I'm sure that laughter was at something else. Okay. So quick review of what we said last time about simple harmonic. Only a physicist would use the word simple like that, just to be insulting. Oh, it's simple, right? So you have something heavy. So you got a mass on a spring. We said, oh, let's solve the equation of motion for that. We wrote Newton's second law. And we realized it's a differential equation, and we guessed the solution, and we plugged it in. We did all that stuff. And we got that the answer, the position along the x-axis as a function of time was a sinusoid. Sine omega, I'm going to start writing omega naught, t plus phi. We said this is the answer, and there's really three parameters there. Right, this is the position as a function of time, so independent variable, dependent variable, and then three parameters. Omega naught is the angular frequency, and we showed you, we did a little shadowgramming to show you that it's the same as the omega in circular motion. It's just in radians per second. A radian can be a trip around a circle, or a radian can be a trip through a cycle. A cycle and a circle are the same. Is that going to fall? Maybe. So that's the angular frequency omega, and for an oscillator, we call it omega naught because we also call it the natural frequency. And that depends on properties of the system, the spring constant and the mass. Then these other two, the amplitude, right, A, and the phase constant phi, those really don't depend on the properties of the system. Those can vary, right? Those depend really on the initial conditions. If I launch this with a large amplitude, A is big. If I launch it with a small amplitude, A is small. And the phase depends on when I launched it, right? So that's why that's the difference. So that was our solution. We were all excited about that. And we said, what can we do with it? Well, we can write V, the velocity. And one thing I didn't quite label last time that is useful in problems, we just took a derivative and said sine goes to cosine, and you pull out an omega. But what we didn't really say explicitly is this is often referred to as V max. This is my cursive V, by the way. That is the amplitude of the velocity, right? The velocity also varies sinusoidally, and it goes from maximum up to minimum down, max up, min down. So the amplitude of that expression, A omega, is V max. And if you really want to get into connections, this kind of looks like if this were a radius and it were circular motion, the tangential velocity is radius times omega. But when we have cyclical motion, the velocity is the amplitude times omega. So similar ideas are flying around. And then we also could write down the amplitude as a function of time minus A omega squared back to sine omega t plus phi. So we showed that as well. And again, you could say, well, this is the maximum acceleration if you wanted to think of it that way. And you could say, oh, it's also kind of like the tangential acceleration was the radius times omega squared. Oh, yeah, kind of the same thing. Okay. So just quick review in case you weren't here. What does the word say ensued the orathithes next to cos? So I don't think I have any room to talk here. This is omega t plus phi. I guess that's not a word. It's a word to me. All right. That's a V. Okay. And then the main thing that the thing I was trying to do to connect it to the exam was we looked at the total energy. And we said the total energy was 1/2 k a squared. We said we could get it from the kinetic. We said the maximum was 1/2 m v max squared. A bunch of stuff cancels and you get this. Or you can get it from the potential of the spring. The biggest potential you have is when it's at a turning point. The biggest compression of the spring is A, so your potential will be 1/2 kA squared. And we saw how it basically just goes back and forth between kinetic energy and spring potential energy. As the thing moves up and down, it's going between those two forms of energy, kinetic and spring potential. Although when it's upright, there's gravitational in there too, but don't worry about that. Okay, so that was it. That's where we were with masses on springs and simple harmonic motion.